What if I told you that time is not absolute? That somewhere above your head, time is literally moving at a different speed, not metaphorically, not philosophically, physically. Astronauts on the International Space Station age slightly differently than we do on Earth. Satellites orbiting our planet experience time in a way that, if ignored, would completely break modern technology like GPS. And the most shocking part? We have measured it. We have proven it. And NASA uses it every single day. So the question is not, is time affected by space? The real question is, why does time slow down in space? And how do we know it's real? Today we break it down using real physics, real experiments, and real space missions. To understand why time behaves strangely in space, we need to go back to Einstein. According to the theory of relativity, time is not fixed. It depends on two things. Number one, speed. Number two, gravity. This effect is called time dilation. Time dilation means that two clocks can measure different amounts of time depending on how they move or where they are located in a gravitational field. If a clock is moving very fast compared to you, it will appear to tick slower. If a clock is closer to a massive object like Earth, where gravity is stronger, it will also tick slower compared to a clock farther away. This is not theoretical speculation. It is a direct prediction of Einstein's relativity, and it has been confirmed in countless experiments, including in space. Even NASA has to account for this every day when tracking spacecraft. Without correcting for time dilation, modern navigation systems would not function correctly. Let's talk about astronauts on the International Space Station. The ISS orbits Earth at about 28,000 kilometers per hour. At that speed, something strange happens. From our perspective on Earth, their clocks run slightly slower due to special relativity. So, in theory, astronauts should age a tiny bit slower than people on the ground. But there is another effect happening at the same time. Because the ISS is far above Earth's surface, it experiences weaker gravity. And according to general relativity, weaker gravity means time actually runs faster. So we have two competing effects. High speed, time slows down lower gravity, time speeds up. In the case of the ISS, these effects nearly cancel each other out, but not perfectly. Measurements show tiny differences in elapsed time. Small fractions of a second over months. It may sound insignificant, but it is real, measurable, and predicted by Einstein's equations. Now we come to the strongest real-world proof of time dilation, the Global Positioning System, GPS. Every smartphone, every navigation app, every airplane, all depend on GPS satellites. These satellites orbit Earth at around 20,200 kilometers above the surface and move extremely fast. Here is where relativity becomes critical. Two effects happen simultaneously. First, because of their high speed, satellite clocks run slower than Earth clocks. Second, because they are farther from Earth's gravity, their clocks run faster. But here is the key detail. The gravitational effect is stronger than the speed effect. So overall, satellite clocks actually run slightly faster than clocks on Earth. The difference is tiny, about tens of microseconds per day. But here is why this matters. GPS works by measuring time signals traveling at the speed of light. Even a 1 microsecond error can create a position error of hundreds of meters. Without correcting for time dilation, GPS would drift kilometers off per day, navigation would become unusable, planes, ships and phones would lose accuracy almost immediately. NASA and engineering teams must constantly apply relativistic corrections just to keep GPS functional. So in a very real sense, relativity is not just physics, it is infrastructure. This leads to a deeper realization. Space is not just distance. Space is also a difference in how time flows. Near Earth, time flows slightly slower because of gravity. Farther away, time flows slightly faster. At extreme conditions near black holes, this effect becomes dramatic. Time can slow down so much that minutes near a black hole could equal years elsewhere. This is not science fiction. It is a direct consequence of general relativity. And we have observed gravitational time dilation in laboratory and satellite experiments, confirming it step by step. So let's bring everything together. Does time move slower in space? The answer is simple. It depends on where and how you are moving. Moving fast leads to time slowing down. Weaker gravity leads to time speeding up. And when you combine these effects, space becomes a place where time behaves differently depending on conditions. We have proven this using atomic clocks on satellites, GPS navigation systems, astronaut measurements, relativity experiments confirmed by NASA and physics research. So the next time you use your phone to find your location, you are indirectly relying on Einstein's theory that time is not absolute, and that somewhere above you, time itself is slightly different. Not science fiction, science reality.